class is being recorded, and this class is the third day of our IT Foundation and AWS Cloud training. In attendance, we have the team members, and we're going to start off from where we stopped last time. And the program is supported by Lockdown LLC. Moving forward, we are going to do a little bit of rehash in the things we did in the past. And basically what we did in the past revolves around some things about hardware. We talked a little bit about the hardware, and I talked about how the computer itself works, how a computer serves as an information storage. We talked about that. We talked about that basically the computer, all it does is to compute. It transforms data from one form to the other. And sometimes information is also known as data. They are data if the particular information is targeted to a particular field. Medical data, health data, scientific data, and all of that. These are information. However, when they are in the data form, they are not statistically. They are statistical. They are not well defined. They don't have that intelligence that's needed. So when they are information which is intelligent and it could be understood by anyone, so there's a slight difference. Although information and data are interchangeable. So we also talked about how the computer computes, and I presented a video by, I think it was Bill Gates was in that video, and I asked you guys to watch it. I don't know how many watched it. And we're gonna continue today. Yeah, we did talk about digital and analog information, but we didn't go too deep into it. And today we'll try to go a little deep into the mathematical aspect of computing. And that's what we're going to do. And we're going to try to finish it off, basically, today. So I also suggest that you take a little time to read some of the documents that we have in Google Play Store. And if you have input, you can also share that input with us, because we are not here to lord it over anybody. So it's a community effort here. The teaching style is one that recognizes others and wants you to participate in what we are doing. Now, if you have not done all the assignment or homeworks that were assigned, you let me know. I can help you do that. The grades is pretty much hands-on. We want you to know what you are doing, not just making grades, because we really want to build capacity. So moving forward, we're going to start from where we stopped the last time. The last time we talked so much about the hardware and software, but we were focusing on the hardware. But today we're going to give you a little bit information on digital and analog information. Does anybody remember what I said about digital and analog information? If you don't, that's fine. I can say what it is again. Does anybody remember?
No.
Okay, so that means I have to go all the way back. Okay, the computer's primary job, it's like I'm starting all over from scratch. I'm gonna make it really fast. Its primary job is, whether it's a room-sized computer, small, little laptop, or whatever, its primary job is to do what? To perform, compute, transform information. Okay? So what it does, it changes, what the computer does has been changing over the time, but basically it will compute information, okay? And it will do it so quickly. It is done very quickly. So what you have to put in your mind is computer just computes and processes information. Okay? So it just does information transformation. That's what you have to put in your mind. What does a computer do? Oh yeah, it transforms information, it processes information, it computes information, all are the same thing, basically. Now, to do that, there are 4 things you need for a computer to do that. 4 major things. You need to be able to input information, and you need to be able to have that information stay in the memory, and you need to have that information that stayed in the memory to be processed upon by a processor, which is called central processing unit, the brain of the computer. And now the fourth thing is that information, after being processed, has to be done what? It has to be displayed on the console. So you have what? Memory, the processor, the brain of the computer. You have the memory, where the information or whatever you put input goes first, awaits for its time to be processed. Okay, while it waits for its time to be processed, the brain of the computer is doing other things. But once it has a little bit of a window called a swap or buffering window, it will just go and grab whatever that's in line to be processed and process it. Okay, so as you can see, there's a need for storage in order for that to happen. And there are two types of storage that I showed you guys. There's the more like I showed you guys about there are two types of memory I showed you guys. I showed the read-only memory, and I also showed random access memory. Somehow these are all storages, but they are short-term storage. Remember when I talked about they are short-term storage. You have read-only memory, you have random access memory, okay? And then you have more like long-term memory, which is like your hard disk, what you call a solid-state disk. So these are the newer form of the hard disk. Okay, so all these things I'm talking about are already on a Google Drive. You can read them on your spare time. But I needed for some of you guys to catch up on what we've done in the past. And then we also talked about information movement. The computer also controls the movement of information from place to place. It reads the information you type in the keyboard, moves it into memory, like I said, eventually displays it on the screen after it's being processed, and you also see them in the file and so on and so forth. So the movement is called input and output. That's the movement. When you put the information and you get the output, is input and output, okay? So like I said before, the computer computes, that's what it does. And then we have the digital and analog information. So for digital information, I told you guys, I gave an analogy that if you are measuring something, for those of us that have children, when they get sick, you remember the old kind of thermometers with the little glass? When you put it on the child, you get a range of temperature between something and other stuff, other numbers. But when you are doing digital, it can only be exact. It can be 70 Celsius, can be 70.8 Celsius, and so on and so forth. But the old way of measurements doesn't, you see a little dot, but that is not specifically exactly, just you have to guesstimate or gauge what the rest of the numbers are. But in digital system, it's more like precise. And that's why modern day computers are using the digital system today. So in that premise, we have the reason why analog died out and the digital system replaced it is because digital system has simplicity and is expandable. Okay, so simplicity, it has to be 0 or 1. That's it. Expandability, you can expand on it. Okay, the error is reduced when a value can be only 0 or 1. So the computer knows there's no value in between. That's expandability in it. It is easy to build on and expand. You can use two binary values together to represent the value of two light bulbs. So a light bulb, you need one to go off. The gate goes to 0. That means electric current is not flowing anymore. The gate goes to 1. That means the gate is closed. When the closed current flows, there's a potential difference, change in voltage. So that is what is happening. There are many gates in a computer, many millions of gates. I don't know if you've done, if any one of us here has done taking a digital class, you will know there are so many gates. This here is a gate. There's also this one. I think this one should be an AND gate. This one is a negation of this one. So there are so many of these kind of gates There's also OR gate, and there's so much different ones, you know. So there's different ones. So say if this one is 0 and this one is 1, okay, and they're going through here, they have to come up with 1. There has to be 1 output, there has to be 1 output, and so on and so forth. So for OR, it means that if it's an OR, that means only one of it has to be true for it to be true. So this is true. Then for AND, 2 of them has to be 1, 1 for you to get a 1 here. So these are some of the mathematics of the computer. Computer only deals with zeros and ones, okay? We'll learn more about it later. But for now, we're just gonna breeze through it like I told you guys. So moving forward now, that's the expandability and simplicity of computer. They are simple because it's zeros and one. Yeah, it's expandable because there's nothing in between. You can build upon it. Okay, you can use 2 binary digits to represent something, or 3 or 4 or 5 or whatever. You can do all of that. All right, so now we are caught up. We can now go into the mathematics of computer. So the mathematics of computer, when you are interacting with the computer, assuming we type this number A, okay, the computer doesn't know what this is, to be honest. The computer go like this, question mark. It doesn't know what it is. So there are controllers in the computer that allows it to understand what it is. First, let's see. There are standards that are built in, like that one is a standard, and there's another one. There's UTF-8 and so on and so on. So let's see the difference here. The essence of the class is for us to use what's around us to learn something. We have to use what's around us to learn something. We don't depend on one source. We attack it from all sources to learn. Oh, somebody's asking if I see a video on my right. Are you guys seeing what I'm showing? Guys?
Yes, I can
Okay.
see it.
Oh, thank you. Thank you. Is yeah, okay, thank you. So like UTF-8 encoded, these are encoded just like ASCII, but we go on, I'll show you guys them one by one. So for instance, we go to let's go to that one and see what we get. I wanted to show you guys something. Okay, this is not it. Let's go back. Let's go to ASCII and UTF-8. These are encoding standards. Okay, this is what we want. Now, I'm going to show you guys what the A stands for, both in ASCII and in UTF. If words come to words, it seems like I'm not getting what I want. If words come to words, I'll just go and do UTF and get what capital A stands for, and then I come back, Unicode transformation. I come back and I go to these are under ISO, International Standard Organization standard of this kind of encoding. They are used in fonts, web, email, and so on and so forth. And many characters, spoken words, the characters of spoken words are used. They also use UTF because they characterize everything that could be written in whatever language, and they give the computer what those represent. Now we're gonna find out sooner than later. Okay, let's go to basic Latin. If we go to basic Latin, we're gonna see something interesting. So for basic Latin, we have da 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 da. Okay, we are getting close to what we want. You see, for basic Latin, this is UTF representation of capital A. We should remember this, okay, guys? Copy. We should remember that. That's UTF representation of capital A. And we're gonna go on and check for ASCII. What is the ASCII representation of capital A? So these are the encoding system that the computer uses to know when you push an A. But one of the prolific and most pervasive one is UTF-8. But before that, we had the ASCII. which is an encoding standard, encoding system, which is normalized by the ISO. I think it has an RFC, which is a comment, meaning that people went through it before it was canonized. So this is Unicode. You can read more about it. Let's go to Ascii now. Ascii is the American standard. So this is a 7-bit character, okay? Ascii is a 7-bit character set containing 128 characters. It's limited. It only has 128 characters. That's why most developers, computer programmers, they don't use it. They use Utf-8. So now let's go to the table and see what A, capital A, represents in Ascii. So as you can see right here, in Ascii, capital A, what do you guys see? This is capital A, right? Hello?
Yes, you can see.
Okay.
Yes, I'm looking.
Okay, so for in decimal notation, that's a 10. In hex, that's the A. But I want to do the letter A. Letter A, letter A, letter A, letter A. Okay, that's the letter A right there. A, B, C, D. No, that's a hex. So let's focus on the decimal part of it. I think that's where I will get what I'm looking for. 65. Okay, I got them. See? Do you guys see where my cursor is?
Yes.
So that's the character A, capital A. So if you are using HTML and you type this, ampersand, you type end, ampersand 65, semicolon, that's an A. Actually, let's try it out. Let's test that. Let's check it out. Let's check it out, guys. All right. Let's see if that's true, and we try that for the other one too. So we're gonna do. Let's just say let's do a half the reference. Let's just write a paragraph. Nothing, no big deal. Just write. Do Ascii. I'm just writing a title just to remind myself what I'm doing. Title, okay. So it's gonna be HTML. Let's just say I copy this one in here. See what we're gonna get. Let's just see what we're gonna get for that. Paragraph. This is something I wanted to do just to see what I get when I type that. So I'll put the other one here too. So let's see what we get. I'll put them in as a paragraph. So the other one is like I think it was something like this, and it was like 65, right? Okay. So if I save this as index.html, I wonder what I would get. Okay, let's see what we get. Okay. I'm just curious about this. I wanted to see what we can get if we do it this way. All right. Yeah, let's see what we get. I'm not sure, but let's see. Don't be afraid to make a mistake. Okay, that one. I think I saved it as this, right? Okay. So you guys seeing the screen?
Yes, I can.
I don't think you see what I'm doing. Need you to hold on. You guys didn't see what I was doing. Okay? Can somebody mute themselves, please? Please?
I'm seeing somebody's face.
Yeah, it's just noisy. So I wanted to see what I get there, but what I got, I wasn't sure what it was. So let me try again. So what I was trying to see is if I can, when I use that notation as a tag in HTML, what I get. That's all I wanted to show it to you guys. Just give me a minute here. Can you mute yourself? Somebody please mute. Oh man. Laban, can you mute yourself? Whoever that is. Oh man. Please mute yourself. Please mute yourself. If you're not ready for the class, maybe you can take another time. But mute. There are people here that are worried about what's going on. Thank you. So all right, let's continue. What I wanted to show you guys didn't work out so well, but the most important thing here to note is this here in HTML is when you type an A on your keyboard, the computer doesn't know what A means. It doesn't. So you need to be processed. In order for it to be processed, there's an encoding system that it uses. I'm gonna write it here. There's an encoding system. Yeah, encoding system it uses. And this encoding system is already canonized or standardized by a group of people under ISO. This is an American organization. It's International Standard Organization. Well, it's not really American, it's international. It's standardized, and we have two of them. One, which is the most current one, is the UTF-8 is bigger than the one that I explained to you guys before. The Ascii is much bigger than Ascii. So let me move this thing away. It's much bigger than Ascii. There's another one. Actually, this is the first one. The Ascii is the first one, but because it's limited to 128 bits, so it's not very well used. For instance, the A in UTF is what you are looking at right there. And then in Ascii, the same A in Ascii, you are looking at what I just showed you, which is and sign, ampersand, and 65. That's capital A. So now, if you're good with HTML, you will know that if you type this in HTML, you should be able to return. It should be able to return A for you. Okay? If you type that, it should be able to return A for you. So I tried to do that, but something went wrong. I don't know if I'm using the right browser or if I did it right at all. But it's something that you guys can try at home and see how it works out for you. But I'm sure you can do it. Okay, that's that. So now, do you understand the encoding thing that I talked about? Hello? Hello?
Hi, I can hear you. I can hear you.
Yeah, but do you understand the encoding mechanism that I talked about when I try to show you the Ascii and also the UTF? I was saying that the computer, when you make an input, the computer don't know what it is. There's something built inside the computer that knows. There are controllers which are encoded to know what you have typed. So I just wanted to see if you guys are following.
Yes.
Okay, in that case, we can move forward. It's just like I'm telling you to learn how to speak English. And then in order for you
Yes.
to learn to speak English, I have to teach you the alphabet, which is from A
Yes.
to Z. The same thing with the computer. The computer has a way of taking whatever language and reduce it to what it understands. So when you are typing that language, it knows each character what it represents because the computer deals with zeros and ones, and we're going to learn about zeros and ones now, okay? So for zeros and ones, what we're going to do is very simple. We know that when you type capital A in the computer get confused. But the question is, how does the computer understand it? So to answer that question, the computer has its own mathematics, okay? If your screen is stuck on picture, all you have to do is refresh your screen and you will see what I'm doing. Please, guys, refresh it, you'll see what I'm doing clearly. So now the computer has its own math, how it understands things. Like you see, we have 10 digits, like we count on our fingers, right? Humans have 10 fingers. And within that 10 fingers, we develop a number system. Can somebody mute themselves? We develop a number system, and that number system is what we are using. So when somebody say, "Oh yeah, 10 digits," 10 digits, it means we're a number system based on how many fingers we have. It goes from 1 to 10, right? Right. So that's the 10 digits. But the computer has its own way. Its own way is the binary system. The computer has the binary system where you have 0 and then you have 1. That's it. But in digital system, you have 1 all the way to 10, right? Basically,
Yes.
it's 0 all the way to 9 to be precise. That's how it works. 0 to 9. So 1 to 10, 0 to 9, 1 to 10. Now, if you have 1, you add 1 to 9, what do you get?
10.
10, absolutely. But
Yeah.
if you have 0 in computer, you add it to 1, what do you get?
So I have to want in digital.
You have to
You get
get 1.
2, 0.
You have to get a 1. But if you have a 1, you add it to a 1, what do you get in binary? So
Binary.
this is being stands for binary. So what do you get here?
1 1 11
You can't get 1 1. Remember, when you add
2, right?
1 to 9, you get 1 0. So when you add 1 to 1, since 1 is the only number that is, you have to get 1 0 again. Isn't that funny?
That's tricky. Yeah.
That's binary. So to prove what I'm saying, we're gonna do a little math.
Okay.
So 1 0,
1, 0.
this is base 2, right? Right?
Yeah. Yeah.
Okay. So now you have 2 raised to 1.
1 is
You're
on.
adding them, right? Plus 2
0 is on.
raised to 0. So you have, oh sorry, 2 raised to 0. Like anything raised to 0 is 1, isn't it?
Yes.
Okay. Anything raised to 0 is 1. Okay. So let me change this. I think I overlooked something. Okay. So 2 raised to power 0, right?
Yeah.
And 2 raised to power power 1. But there's something going on here I need you guys to understand. You see, this 0 here means that this guy is not on.
1 is on.
You get it?
0. Yes. 1 is on and 0 is off. Yeah.
1 is on and 0 is off. You got it.
Yeah.
That is so smart. 1 is on and 0 is off. So since you have the idea now, let me expand on that so that every one of you will get it. Let me expand on that. Okay? Let me expand on it. So now let's do this. We go 0.
0 is off.
Go 1. Hold on. Don't move too fast. We'll go 2.
2, number 2.
We go 4.
4.
Go 8.
8. Okay.
Go 16.
So 0.
Let me write it right. Let me write it the right way. Sorry guys. Let me just wipe everything out. I need you guys to understand this part. This part is very important.
Yes.
All right. So I'll write it so that everybody will get it.
So 1 is on, 0 is off.
Give me a few minutes here so I write it correctly. So 0, 1,
0 is off.
1. This is an example, right? This is an example that we're gonna give. So here you have 1. Pay attention, guys. Pay attention, please. You have 2, right? You have 4. You have 8.
1, 2, 4, 8.
You get it? Now,
1, 2, 4, 8.
now you have here. You have 16.
Oh man.
You have 32.
I know how to do this.
You have 64. You have what? 128.
0, 2.
All right.
What is that? Yes.
So you have 1, 2, 3, 4, 5, 6, 7, 8. So
Yes.
this means that if you turn the 1 on, what do you get? You have 1 here.
Yes.
1 second. If you turn the 1 on, that means you're gonna have 1 here, down here. And if you turn the 1 off, you're gonna have a 0 here. Like this one here is turned off, so you have a 0 here. This 2 here is turned on, so you have a 1 here. And then this 4 here is turned off, you have a 0 here. And this 8 here is turned on, you have a 1 here. That makes sense?
Yes.
And
Yeah,
right here,
it makes sense.
all these one are turned on. They're all on. They're all on.
So we
Okay? So now let's focus on what we just did. Remember, we did 1 plus 9, and we got a 10. And I ask 1 plus 1, what do we get? Somebody say 1, 1. And I said, well, in the digital decimal notation, we know that 9 is the only number that you can have before you get a 10. And then in binary, we know that 0 is the only number you can have before you have a 1. Before you can get another 1. But now I'm asking you to add 1 and 1 together, just like we add 1 to 9. So if you do that, that means you're gonna have 0, 1. Because you cannot write 2 in binary. So 1 plus 1 is 2, but you cannot write 2 in binary. It's not possible. Does that make sense? Does that make sense? You cannot write 2.
Yes, it makes sense.
Okay, you cannot write 2 in binary, but you cannot write like 2 in binary. No, you are doing binary notation. It's impossible to write that. So what you do, you put 0 and carry 1 over. See? Then you have 2, because right here is your 2.
What do you mean when you say you carry it over?
because you cannot write, you can't write 2. It's binary.
Right.
It's limited to 1.
So do you keep it, or you just keep it in your mind that it is?
You keep it in your mind, is this place is 0, and then you carry the 1 over. So you have 2. So that becomes 2. You see?
Yeah.
Now, if you are following the same instruction, it simply means that 1 plus 1 plus 1 will be equal to what?
1 plus 1 plus 1 plus 1 is 2. 1 plus 1 plus
1 plus 1 plus 1 should be equal to this.
1 plus 1 plus 1. 1 plus 1 plus 1 is 3 ons.
Because if you go here, if you turn the 1 on, you have a 1. If you turn the 2 on, you have another 1. So when you add it together, it's a 3. So 3 is like 0, 0, 0, 0, 0, 0, 1, 1. That's a 3.
Yes.
That's a 3. So can somebody tell me what a 4 is? Let's work together, guys. Let's work together here, guys. Please.
Can I try? Can I try, Josiah?
Yeah, you can try. You can teach us. If you know this,
I might
teach
be
us.
wrong. Okay, I'm not that good at it, but okay. So a number 1 equals on, and number 0 equals off. So
Correct.
if I want a 4, I need 4 ons because 1 is on. So I need a on. So in order for me to do in order for me to do a number 4, I need 1 plus 1 plus 1 plus 1. That should be 4 because I think 1 equals on and 0 equals off. So because 1 equals on, I need 4 ons. I hope I'm saying it right. Right?
Well, you need 4 ons, but you already have 4 here.
Oh, I do. Okay,
You
so it's
already
already.
have 4 here. Why don't you just turn that 4 you have on, and everything else will be off, 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 off.
Oh, I see. It's like the electrical switch.
That's right.
Oh yeah, because
So
like my
now
phone is
everything else is
on.
off and 4 is on. That means 4 is equal to
Mhm.
like decimal 1000. Are you guys seeing what's going on here? 2 is like 10.
2 is like 10.
Yeah. Oh, sorry. I made a mistake here, guys. This is did somebody notice, did anybody here notice what I've done here? There's a slight mistake in notation. Did
Which
anybody, let me see if anybody's paying attention.
let me see. 0, 2. 2 plus 2 is 4. 4 plus 4 is 8.
I
8
made a
is 8 is
mistake here.
16.
This is not where the 1
16.
is supposed to
15 is
be.
16 is 32.
This one is not supposed to be here, guys. Please pay attention, guys.
Oh, I didn't.
Okay, that one is supposed to be here.
Um,
That one is supposed to be on this one, guys. Get it? It's just the way I
yeah,
wrote it, guys. It's the way I wrote it. Okay, let me make it in such a way it will be distinguished.
yeah, I like the red. I can see better.
So you guys can see better. Okay.
Yeah, that makes sense.
You see?
Yeah, it's a 4.
So now the one we did before, a lot of people are not responding. I have a feeling they are missing it. Okay. The one we did before, let me line it up properly so you guys get it. See? Does it make sense now? So this is for 4 is like when you write 100. It's like when you write 100 in a decimal. Make sense, guys? Does it
Yeah.
make sense?
Yes, 400.
Let me try to align everything so that other people can understand.
So 1 plus 1.
It's kind of hard to write with what I'm writing with. I'm not on a surface or anything. I'm just on a regular. Okay. Okay. Can you guys let me know how you guys feel about this, please?
Yes.
I have no idea about this, so I'm just listening to understand and taking notes.
Okay, I need you to work with me. I'm gonna make you have the idea. That's why I'm lining everything up so you guys will have the idea. Now,
Yes.
what we are saying here is the way that the math for the computer is done is using a gate. It's zeros and ones. That's a video I sent everybody to watch. It's zeros and ones.
Yes.
There are thousands, billions of gates that are performing operations. People that are smarter than us knows how many times all these gates had to come and open and close to formulate what they call to represent the something. Okay, they know how many times, like in most CPUs you have quad core processors. These are in gigahertz. There's billions of flip and flopping that's happening. So now in encoding systems, we do know that ASCII is used for encoding. When you type a letter on your keyboard, that letter is now moved to the processor. However, it goes through a controller. The controller knows that you typed in something. But then the brain of the computer has to process it in context to give the meaning that's needed. Okay? So what we are trying to show you here is that the way the computer does the mathematics is all zeros and ones. That in binary notation, you cannot have 2 in binary notation. It's not possible because the cutoff is 1. Everything is represented in 1 and zeros. So I was trying to show you guys how the computer actually does it. Then I started off by identifying few things as a precursor of what is to come. So I did identify 1. I did identify 1 to represent how it's gonna go down. I identified that up to 128. And when you add all this, when you add this, all of it, when you add all of this, okay, you get I think you get 256. When you add all of that, you get 256. So now that's how computer represent everything that is gonna deal as zeros and ones. That way you can take it back to the decimal notation, and that way you can
Yes.
bring it forward to the binary notation. For instance, if I write 2 here, if I write a 2 here, let me go back and write it. If I write a 2 here, it tells you that it's a base 2, right? Right?
Yes.
If I
Yes.
write a 2 there, it tells
It's
us that it's a base 2. But then we do know that if you raise a 2 to 0, you get a 1. And if you raise another 2 to 1,
2,
you get a 2.
2,
And if you raise another 2 to a
2
2,
to 2,
you get a
2
4.
times 2,
All right.
2 times 2 is 4.
Guys, pay attention. And, you know, there are other people, respect other people, you know, so that they don't have to hear what you're saying. Guys, pay attention here. This here is this. This here is this 2. And this 2 here is this. It's just math. Okay?
Okay.
Let me do it again so everybody will understand. I use red. I use this red. Just let me know if you lost me. Please, it's important for me to know this. So that's that. And let's use another color for this one. Okay, that's that one. It's not giving me what I want, but it's okay. Okay. This one now is gonna go to, I believe, this one. Just making sure the colors are different. Then this one is gonna go to, I believe, that one. All right. So these are what I'm trying to show. So 2 raised to power 0 is 1. 2 raised to power 1 is 2. And 2 raised to power 2 is 4. This is binary. So now if I turn this one off and turn this one off, and I get only 2 raised to power 2, which is 4, as I showed you guys here, this 4 is on. That's why we put 1 for the 4. And everything else is 0. Everything else is 0. Okay? Like for the 4, everything is 0. Everything is 0. Okay? That's a 4 right there. Now, can somebody do a 5 for us? Now that I made it so simple, so can somebody be confident enough to do a 5 for us? I'm showing that 4.
I can try if nobody else wants to try.
Yeah, somebody's gonna try. I think somebody will try. Let's give other people a
Oh,
chance here, because
okay,
it's important
sorry.
that everybody understands
Okay,
this.
sorry. Okay, thank you.
Is that 32?
You mean 5?
Yes.
It can be 32. What do you have to turn on? Check what you have to turn on and what you have to turn off to get a 5. Once you check that, it's easy. You figure it out. Is Aziat here?
I believe she's there. I believe I marked her present. Unless yeah, she's here.
Can somebody try?
I can try if no one else
Okay.
wants.
Okay, try. Go ahead, try.
Sorry. Okay, so since I want a number 5, and I know that all ones are on and all zeros are off, that means I need a 5 and a 0, because that make either a 5 and a 0, or I can use a 4 plus 1, because both of those mean 5.
All right.
So
you're saying, what you're saying is turn. You're saying to turn 4 on, and then
I could,
turn 1 on, and
yes,
turn everything else to 0.
I think, because if that way doesn't work, then I can do the 5 and 0, because they both equal 5,
This
I
only way
believe.
that works is the right way. This is what works. Everything else is
Yeah.
0. That means
Yes,
you
so it
have
would be a
4, you have 1,
4.
that's a 5.
Yes.
I need
And then
everybody to get this. We're not moving an inch if nobody else gets this. We're gonna be stuck here. Can somebody do a 6 for me?
okay, a
And another
6.
person do a 7, and another do a 8, another one do a 9. It's right here. It's open season, guys.
I think you got to count 4 and 2, and then everything else is 0 for 6.
Please teach me again. What do you want me to do for 6?
Turn on 4 and 2, and
You
then
want
the
me to
rest
turn
are
on
0
4 and 2?
and 2. Yes.
Yeah,
Wow, you are so brilliant. Why are you keeping
yeah,
quiet all this while?
that's good.
She's brilliant. She was just watching us. She didn't want to say nothing. All right, guys. So she's right. So let me turn all this. She told me to turn all this off, and that's exactly what I'm doing. See?
Yes.
I'm doing exactly what she told me to do. And it seems like she's right. This is 4, this is 2,
Yes.
and that's a 6. Can somebody do a 7?
So for 7, you would turn on.
No, somebody else, not the same person.
I'm a different person.
Oh, okay. Your name, please?
Hannah.
Oh, okay. Go ahead.
So for 7, then you would turn on 4, 2, and 1.
Wow, that's amazing.
Yay! Ding 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 ding.
4, 2, 1. Wow, I'm glad everybody's getting it. I'm so happy, so excited. So this is the secret of doing computer. If you're telling somebody, "Oh yeah, I can do computer," but you don't understand how it works, it's useless. Makes no sense. So can somebody do an 8?
I can try them.
Go ahead. I like that. Don't be afraid to make a mistake.
Okay, so you turn on 8 and everything else is 0.
Okay. Wow, I like that. Very straight to the point. You turn on 8, everything else is 0.
Yes.
You see how easy that was?
Yes.
That's how
Ding ding
how
ding.
easy computer is, and that's how easy the program is too. Once you get the pattern, you're good to go. And this is like writing 1,000. So let me show you guys the pattern. Okay. So remember when we did 2, it's like writing a 10. Remember when we did 4, it's like writing a 100 in decimal. Remember when we did now that we just did 8, it's like writing like 1,000. Now this is the trick. This is 10 raised to what? This is the trick. This is 10 raised to what? 2. This is the trick. This is 10 raised to what? 1. Now this is 2 raised to power 1, like I'm showing you guys, right? And this is 2 raised to power 2, like I'm showing you guys, and this is 2 raised to power 3. Do you guys see the pattern?
2.
So this one is binary, and this one decimal.
Decimal.
Does that make sense, guys?
Yes.
All right. So if that makes sense, I need everybody to say it makes sense, please. It gives me joy when it makes sense. And then I know I can move to the next class.
It makes sense.
Okay. So now, remember I talked about Ascii notation? Like Ascii. And I told you guys that in Ascii, capital A, oh, sorry. I'm supposed to do this, not that. That capital A is actually assigned to 6.5. Can somebody do a 6.5 for us so we see how the computer plays with the 6.5? I'll go ahead and lay it out for you first. That way you can do it. Okay, I'll lay the foundation for you. So this is how you lay the foundation. So that way you can get any number in binary. So you start with, like, you write a 1, you write it. Oh shit. Sorry about that.
16 plus 8.
Okay, you write a 1.
14 is 24.
You write it
So
2.
68.
Write a 4. Write a 8. That's laying it out. You write a 16. You write a 32. Write a 64. You write a 128. And now you know that A is 65. Now how do we make the computer, like, how does the computer read A? I want you guys to show me. Let the brave person show me.
8, 42. So I need to make it 65.
What do you turn on to get a 65? Remember, these are all gates, different kind of gates, the NAND gate, the OR gate, the exclusive OR gate, and all that.
So you would, can I speak? It's Hannah.
Beg your pardon?
Can I try? It's Hannah.
Yeah, go ahead. Oh, Hannah, go ahead.
So you would turn on
Can somebody
64.
mute? What do you want me to turn on?
64.
Is on.
And and 1.
Okay, we turn 64 on here, and we turn 1 on here, and the rest are what? 0?
0, yeah.
The rest are 0. Okay, let's turn the rest. You see, I'm doing exactly what she told me to do. And let's see. So this is what the operation the computer will perform. The computer will do this amazing thing. It will do, this is a NAND gate. This is negative gate. This one is exclusive OR gate. This is OR gate. This is a NAND gate. You guys should watch that video, guys. So if you have 1 and 1 enter this gate, 1 will come out. If you have 1 and 1 enter this gate, 1 will still come out. If you have 1 and 1 enter this gate, this is interesting. 0 will come out. If you have 1, and well, negation is like the opposite. So 0 will still come out here, right? So it's negation, negative. Actually, it takes 1 input. Sorry, guys. This one takes 1 input. So if you put a 1, what you should expect to come out would be a 0. Okay, that's how it works. The negative aspect of it is you're flipping the bits for the negative. So we're not going to go deep into that, okay? All right, guys. So now we have done 65. Let's go and find something else we can do. Let me see if there's something interesting we can do to enhance our ability and to give other people chances to do something. All right, let's try delete. Delete is 127. So now I entered delete. I want the computer to delete something. I entered delete. Delete, and delete is assigned to Ascii. It's assigned to what? Ascii 127. Can somebody tell us how the computer will do this delete? I can't wait. What numbers do you add up together to get a 127? Those are the numbers you turn on. Can somebody tell me?
Can I try?
Sure, why not?
Okay, so I need to delete 127.
There is no
So
delete is the same thing as HTML 127. That's what I'm saying.
so I think that I would have to turn on I think that I would have to turn on 2.
No,
1.
why don't you do this? Why don't you find out all the numbers that you can put together to get 127? Why don't you do that first?
127.
So once you do that first, then you turn them on one by one.
Oh, okay. Okay, thank you.
So
I don't see.
Can somebody else try, please?
I think just turn off the 128 and everything else zeros and everything else 1.
Oh.
But we're looking for 127.
Yeah.
I think, can I answer? I think that we click 128 and then somehow we minus 1.
That's flipping bits. That's a better way to do it.
Can I try, please?
Yeah, go ahead.
You would turn on 64, 32, and 1.
Okay, let's see what you say. Who's this, Hannah?
Yeah.
Okay, let's do this quickly. See if Hannah got this. 64.
Because I only got 97.
What else do I turn on?
Wait, am I wrong?
I only got
didn't say
97.
you're wrong. I'm just saying I'm following your command. I turn on whatever you tell me to turn on, and then we add it.
Let me try again. 64.
1 second. I think Hannah is doing something. 1 second.
I recalculated and it only comes out to 96 or so. So I'm going back and re-looking at it.
Okay, can somebody else try then?
I believe Jerry was right. You turn 64, you turn on, 32, 16, 8, 4, 2, 1, and then 120, you turn it off.
This?
So every,
Is that what you mean?
Yes.
Let's add it and see if you get 127. So 64, 32 is 96. So 96 plus 16, 102, 112.
112. 112.
So you're correct. This is correct. So this is how the computer know is a del. Now the del, now this thing that you see here, let me show you guys a UML diagram, not a UML diagram, rather an architectural design of something. So you have this, you have this as the ASCII, right? Let's say you have this as ASCII. All those characters are represented here. And let's say you have this as a del. So now the del has to be looked up inside here. So the controller already has the ASCII. This controller has the ASCII in here. Whatever the keyboard or whatever has it in there. So that when you type the delete, it takes that input, put it in memory. When it get processed, you get looked up in here and it matches what you typed. Okay? So this is, first of all, when you type delete, it goes to the memory. Okay? So all of this goes to the memory. Then the processor processes what's in the memory. So let's say you have this here is the memory, and then this one is the processor. Okay. When you type delete, it goes. When you type the delete, it has to go first to the memory for sure. The delete code will have to be sent to the memory. Sorry. I'm not used to writing with this thing, but I will try. It gets sent to the memory and it's given an address here in the memory. Okay, it's given an address in the memory. That's how it works. So when the processor is ready, maybe the processor has time now to go and see what's there. When it's ready, it will now process that address. Maybe that address is represented by something. Let's say, what can it be represented with? Let's say it's represented by maybe by this, 1, 2, or something. So the processor will process whatever that's in there. And when it processes it, remember the flip-flop, the gates, based on the off and on what is turned on, then that information now gets back to the controller that's on the keyboard where the delete was pressed. And now, when it gets back to the memory now goes back to where the key was pressed, and that then is displayed on a monitor. So you get the delete function where you can delete, maybe it's a file, so you are deleting those files and stuff like that. So the idea is this controller here is built into the system, and it has encoding, ASCII encoding. You also have UTF, like I explained to you guys, that's another one. It's bigger than ASCII. ASCII is the small boy. The UTF is bigger. It covers a lot of characters, which ASCII cannot do. So I'm confident that you guys have figured out the math of the computer and what the computer is actually doing behind the scene. Do you guys need a break for like 5 minutes and we'll come back and wrap this whole thing up?
okay, sure.
Like just
Yeah.
5 minutes and we come right back. Because I needed to do something.
Hello?
Yes, I'm right here.
Hello?
Yeah, if you wanted to say something, go ahead. I'm right here.
I think she's on her cell phone.
Oh, you have to mute yourself, guys. Mute, 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 mute.
I did mute myself. And now?
Yeah, it's your phone.
I did mute myself. It says I'm muted. And now? I did mute myself. Now? What? Am I mute? Okay.
So everybody back?
Yes, I'm back.
Everybody, I mean, we are a team. We work together. We have to
Sorry.
take care of all of us.
Yeah. Here.
I'm here.
Okay, good to have you back. So now, before we continue, I found a really cool website that I wanted to introduce to you guys, right? So this is a really practical way of learning. We learn by doing it, not just, trying to cram it up and just impress other people that we know. We actually want to do it. I want to work together with other people who wants to know how to do it at the same time. So I found this cool website, and what we're gonna do now with this cool website is to play out the ISO standard and how it's being noted in both HTML and UTF-8. Because when we talk, I don't just want to talk. I want you guys to know it, to see it in action. All right. So this website, I'm gonna post it up here. It will be something you guys be playing with when you get home. Hopefully, it will help you to gain more understanding. And it's a cool website, You will love it. To show you all those things, a little bit of those things I'm talking about, how you can represent them. And I'm not gonna leave you without actually demonstrating something. So I will go and find something useful that we can demonstrate it with, which is the character codes list. So I'm gonna go to basic Latin and find the one we are about to use. Okay, I found this one. This one. Okay, this one is not the one I'm looking for. I'll find another one. Okay, I think I found what I'm looking for. Okay, this one. I'm gonna try it. This is a cool website. I think everybody should try this cool website. I'm telling you, you guys are gonna love it. You guys will thank me after trying this cool website. So the website shows you how to put the Unicode and HTML and see it in the browser working. Not just me telling you. You see it yourself that it works. That's the beauty. So you will go ahead and see what I've done, and you also see what the website has done. I will show you guys that. I'll show you what I did and what the website did, so that way you see that we're all speaking the same language in a different way. That's amazingly great. That website is so cool. I'm glad I found it. It will help you guys to get your game on and HTML and all that kind of stuff. You guys are gonna love it. It actually encourage you guys to start doing stuff in HTML without like being afraid, because now you know how it works or how it should work. You kind of have an idea of what's going on. You know. So this is the best thing I've ever found today. This website. What do you guys think? You guys haven't even checked it. Well, when you check it, you see. you see for yourself. Okay. So let's go ahead. Let me show you guys what I got, and then you can see. Can you see my screen, guys?
Yes, I can now.
Okay. So you guys remember when I was trying to do type it out some of the stuff, and I wasn't sure. So I finally went back within that 5 minutes, and I came up with some stuff in combination with what I showed you guys on the website. And now I put together this little lines of HTML codes. I put it together here. I demonstrated for one, when you look here, that unsigned ampersand X41, that is equivalent to capital A, capital letter A, as I can show you on that website at the same time. Now I put a break, okay? I put a break. That break there shows that I'm gonna give some spaces between this A and this other A, all right? So this one A is here and that other A is here. So it's gonna be two A's. But if you notice carefully, you're gonna see that one A is UTF encoded and the other one is ASCII encoded. That makes sense, guys?
Yes.
Then I saved it as an index.html, which means I'm gonna open it as a HTML text and it's gonna display as a HTML. Okay, it's gonna display as a HTML because in W3C they use the protocol for HTTP communication, hypertext transfer protocol. That's what they are using, and that involves HTML. That's the markup language, hypertext markup language that is being used. So I put this command in the hypertext markup language, as you can see here, and then I saved it as index.html. Now I'm gonna open it to see what we get. So when I open it, I hope it opens here. If it didn't open here, then I'll move it to here so that you guys will see it. I'll crop it right like that, and I'll go ahead and do like that. See, like that. So when I click on this, that's what comes up, but it's already up. See, class for cloud movement. Remember, I wrote that here. Class for cloud movement. I can say day one.
Wow.
I'm basically showing you how we manipulate the computer with higher language to make the computer do small stuff that we want it to do. So the developers or programmers or coders, that's what they do. We write high level languages, then the computer takes it down to encoding and all that stuff and writes it down as binary. So the UTF character is writing it straight as binary, not hex. That's why I love UTF and I use it in a lot of things. It's going directly as a binary, see? So now when we go back, now whatever I typed in on a higher level, the computer doesn't know what that is. It doesn't. Then when I run it, now it knows what it is. Now it displayed on my screen. Do you guys get it?
Yeah, I get it.
So as you can see, it's so easy. It's not difficult. The computer, the so-called computer stuff is easy. It's not difficult at all. As you can see, I have two A's here. One A came from the UTF, and the other A came from the ASCII, right there. See, we write high-level languages or high-level stuff to communicate, use it as an interface to communicate with the computer. And the computer actually does it in a binary, zeros and ones, because all these things here are represented by a number. So we have A to Z and the A, capital A, is 65, and so on and so on. So that means Z is gonna be plus 25. So it's gonna be 65 plus 25 is gonna be 90. Z is 90. Okay, so for instance, if we let's see if I'm correct. You can change this to 90 and see what we get. No, not that one. This one to 90 and see what we get. Okay, guys? See, I'm not afraid to make a mistake. If I make a mistake, I try again. Am I correct, guys?
Yeah.
Yes.
So don't be afraid to make a mistake. The idea is for you to know what you are doing. Know what you're doing. Oh, okay, 65. Okay, 65 is capital A. That means, oh, the alphabets are 26. So I've already taken one out of the 26. So if I add 25, that's gonna be Z. That's how computer people think. That's how IT professional engineers, that's how they think. They think so fast, using numbers. Everything is number in the computer world. That's why I'm doing this program. Once you understand this magic of numbers, man, your career in computer field will blossom. You will do well because you understand how it works. You're not doing it because of the money. You actually know that the computer is dumb. It doesn't know nothing. You put input, something has to process it, which is the brain, and that thing has to be stored in the memory at first, which is short-term memory, read as random access memory, and after this processor processes it in context, meaning that there are other stuff before that. It gets to that one, and it delivers the output, and now you see it in the console, just like we see it here. This is practical training. You see it happen, and it's real. So we are done with that, and we've done with the mathematics of computer. But before we wrap it up real quick, next class will be really fast. We'll move really fast to the next class. The homework for this class will be just to read, to watch the video and play with this website. That's going to be the homework. So next class, we'll move really fast. We'll do a little bit more of the mathematics of the computer. And before I leave you guys, I wanted to show you guys some identifying marks for hex and binary. So you have prefix and suffixes, like when you see somebody write something like this. It's important that you guys know this. When you see somebody write H, oh my God, H, maybe B5. Don't forget, this is in the syllabus. So this is not 13. This is actually B5. Sorry. This is the same thing as when you see somebody write this, B5. And it's still the same thing with this one, which is also redundant. Can you turn that up? Thank you. So all these things are the same thing. So they are saying, basically, I'm saying that this is a hexadecimal number, meaning it's in base 16. Then when you see something like just bean, can somebody tell me what this one is? Bean. Bean is another way of saying binary, right? Why is everybody keeping quiet of me? What did I do?
You can hear you.
We're listening.
Oh, you guys can hear me or not?
Yes, we can hear you.
Yes, yes, I can hear
So
you.
when you see the bean, it's just binary now. Bean 35. Can somebody tell me what it is? It should be 1, 0. This is 8. This is gonna be another 0. So 32, 35. So we give it a 3. I mean, sorry. We give that one is gonna be, oh sorry, Sorry, guys. So this is 8, 0, 4 is gonna be 0. 32, you have to have 2 and 1, right? So you have to have one here and another one here, right? Let's check it. Let's check it to make sure it's correct. So we know that this is 1. We know this is 2, right? We know this is, oh shoot, what am I doing? Sorry guys, I've been written with this. I have to change this thing. Maybe I should buy a surface. Okay, you know this is 4, right? And you know this is 8, right? Maybe I'm wrong. This is wrong. It's supposed to be here.
32. Wouldn't it be easier
It's supposed to be
just
here. This one is supposed to be 0 too. Okay, guys?
Yep.
Now it makes sense, isn't it?
Yeah.
I have to put a 0 there. Give me a second. Okay, I have to put a 0 right here. So now it makes sense, eh? Right, guys? So before
Yes,
we
it
go,
makes sense.
so I want to make sure that you guys understand this. When you see that 0x, that's a binary. I mean, that's a hexadecimal. And when you see the 0x is the same thing. When you see an H in the front, it's also the same thing. But before we go though, I wanted to introduce 0, 1, 2, 3, 4. This is the shorthand. We're gonna learn this the coming on Tuesday. This is the shorthand for binary that computer uses to make something move really fast. Okay, this is A, this is B. Some of you know this, some of you don't. Anybody knows this?
No.
So this hexadecimal notation is start from 0 and ends as F. These are 16 in number, and they are used to represent things. For instance, the number this here we can use the hex to represent it. I'll show you guys how. So this is 32, this is 64, this is 128, right? So I'll show you guys how you can use this to represent something in hex. So in hex, the way you do hex is different. In hex, you attack it like this. They are called, this is called a nibble. It's called a nibble. So 2 nibbles will make a byte, and a byte is the size of a character. I'll show you guys that next week, but I'm setting you guys up for next week. So for 35 is gonna be, what is this? This is 01, 011. So it's gonna be 35 also. It's gonna be 3, 5, okay? That's for hex. But this is where it gets interesting. Assuming you have a number bigger than 35. So let's say we have, can somebody come up with a big number we can play with here? Like 192? How can we represent a number that is bigger than 128? A number that is bigger than, let's say 3, 4, 6, 7, 8. Okay, a number that is bigger than 99 or 96. How can we do that? We have to use the hex. So now let's say we have, okay, let's say we have 96, okay? And I'm gonna lay it out for everyone. So we have 128. We're looking for that. 128. We have, so we should have 64 here. 64. We should have 32. We should have 16. Should have 8. Should have 4. should have 2, should have 1. So 96, we already know we have to turn the 64 on. We already know we have to turn the 32 on. Everything is gonna be 0, guys. So now we do this and we do that. So here is interesting. So what does this look like to you guys? Is it on 60, right? 60, right? Right?
Yes, yes,
So
yes.
now 6 times 16 is what?
16 is 36.
96. That's
Yeah.
how it works. That's how it works. So here, actually, this one here is supposed to be 2, and this is 3. Do you guys notice a pattern there? Oh no, there's no pattern here. So this is how we do it, okay, for hex. So you take it by the nibbles, half a byte, and you identify what this one is and you identify what this one is, and that's that. Then there's also bigger numbers to do, which will fall into like letters. Like if you do something more than 9, it fall into letters. Maybe we try to do 128, 127, 196, 132, and all of that. They will start to fall into letters. Once you have this thing more than 9, see here, more than 9, then they fall over letters. Let me see how I can make you guys understand it. Once this one goes more than 9, 9 times 16 is what? Let me see who's gonna catch it. Hurry up. Please hurry up.
9 times 16.
Yeah.
144.
Thank you. So assuming we do 144, you're gonna see something amazing happen now when we do 144. So to do 144, we know we gotta turn 128 on, right? 128, turn it on. After we turn 128 on, what do we have left? 16, right? Right? So 64 is gonna be turned off. 64 is gonna be turned off. 32 is gonna be turned off. 16 is gonna come on. 0, off, off, off. This 144, right?
Yes.
Okay. We take it like that. So here is 1, here is 8, this is 9, right? 9, 0. Now, from what we've done, the hex for 144 is 90, but we want to do something bigger. That way, I can show you guys how this thing changes. Let's do something like 145, right? Yeah, 145 would be bigger. If we no 145, that means it's not that big. We should do something like 192. Okay, let's do 192. Let's do 192 and see what we get. There's something I'm trying to show you guys. Just be patient. You're gonna get it. Once you get it, you're gonna be happy. Okay, let's do 192, right? Okay, we know that 128 is gonna turn on. What else is left? 64? Okay,
Yes.
it's gonna turn on. The rest is gonna go 0, 0, 0, 0, 0, and 0. But we still have to do this. So what we get here, because this is 4, this is 8, this is 12. Can somebody tell me what we gotta put here? This is 12. Remember, this is 8. This is 4. This is 8. This is 4. Together, they give you 12. But it's base 16. Remember, I showed you already how base 16 goes. So that simply means this is 10, B is 11, C is 12. You guys following? 13, 14, 15. So what is this? What should I put here for hexadecimal notation? Hurry up, please. What should I put there? Remember, A is 10, B is 11, C is 12. What should I put here? We already know that this one, all this here is 0. We know that. So what is this one, guys? Please help me. 8 plus 4 is what?
12.
So what do I put here?
C.
C. So this is hex notation. This is 0 times x, or h c 0. You can check that on Google. So we're gonna end the class here, and I really appreciate you guys showing up. And I want you guys to know where we stopped today. We stopped on the mathematics and computing, right? That's where we are wrapping it up. And we're gonna continue expanding on computer instructions. I'm gonna show you guys an example of the computer instructions, although I showed you guys a little bit with the HTML that we did, but we'll continue to wrap it up, finish it all up. So when we come back, we're gonna start on human instructions. Yeah, we're gonna start on human instructions. We're gonna do a little bit more from the human instructions and computer instructions. We continue with computer instructions. Okay, guys? I really appreciate you guys making it to the class. And basically, the homework is not complicated. It's just to watch the video on how computer works, and also to play with the website HTML and write a little bit of code showing me how UTF work and how HTML works. You choose whatever HTML that you like I've shown in like I've shown you guys here. You just come up with whatever you want to write with the HTML and the UTF code notation, following what I've already did in class. You write whatever you like. If you want to write your name like here and all that, go ahead and do that. I'll be more than happy to see it. If you want to write your name with binary, all binary, converting all your names to binary, be my guest. Go ahead and find out what your name is in binary and write them all out. If you are finding it difficult, just hit on try it. You see how they did it, and you do the same thing. So we're learning all the core of IT. I call it IT foundation. We are learning together, showing one another how it's done. So that way, when we go on an interview, we say, yeah, of course I did it. I know how it's done. This is how it works. I can even go ahead and demonstrate how it works. And that is knowing the thing, not just cramming it up to pass the exam. So this is what we're gonna do, and that's the homework. I hope somebody noted all this down. I am gonna sign off now. Thank you guys immensely for being part of the program. I really appreciate this. You guys make me happy each time I see you guys come up here. So for those that didn't finish the homework from last time, please contact any of your team members to help you out in it. And the videos are gonna be edited and uploaded so that those that are absent today can get it. Thank you guys again, and enjoy your day.
Thank you.
I'll show my face one more time before we go. All right, we're done.